Our planet, Earth, a sphere of rock and water, teeming with life on its skin, but beneath this familiar surface, vast, hidden realms await, secrets locked deep within. We are by nature explorers, driven by an insatiable curiosity to see the unseen, to know the unknown. What is this quest called geophysical exploration? Think of it as planetary science, giving Earth a thorough checkup, using the fundamental laws of physics to peer into its mysterious interior. We cannot simply dig everywhere. Imagine the scale, the cost. So we use clever indirect methods. Science becomes our deep-seeing eyes. Why embark on this journey underground? Vital resources lie hidden there. Water, the essence of life, energy to power our civilizations, minerals to build our world. Understanding Earth also means safety, predicting earthquakes, volcanic moods, building resilient cities for tomorrow. It's about our connection to this world. Many tools are in the geophysicist's kit. They measure the subtle pull of gravity, they map invisible magnetic fields, they trace pathways of electric currents, and they listen to vibrations, sound waves traveling through the Earth. These are seismic methods, among the most powerful ways to hear the Earth's ancient stories. So, what is this seismic method? Imagine you have a giant drum. You give it a gentle tap. You listen to the sound it makes, the resonance, the echo. We do something quite similar with Earth. We send a controlled vibration, a tiny man-made tremor, a seismic wave journeying downwards. How do these waves reveal secrets? As they travel into the Earth, they encounter different types of rock, different layers, different densities. When a wave meets a boundary, part of it might bounce back, an echo from the deep, or it might bend, changing direction, like light passing through a lens. Each material leaves its signature. We deploy listeners on the surface, highly sensitive electronic ears. On land, we call them geophones. In the vast oceans, hydrophones. They patiently wait for the returning signals, these echoes from below, recording precisely when they arrive and how strong they are. This data is a coded message from the Earth's hidden architecture. All this information, these echoes, are pieces of a grand puzzle. Scientists use powerful computers, sophisticated algorithms to process the recorded wave patterns, transforming them into a picture, a map of the subsurface world. It's like creating an ultrasound image, not for a tiny human body, but for our entire colossal planet. There are two main ways we use these waves. The first is seismic reflection. Think of it like looking in a mirror. The sound waves travel down. They hit a boundary between rock layers and bounce directly back up to our waiting sensors. This technique is superb for imaging. It shows the shape, the depth, the detailed structure of these layers. The second method is seismic refraction. This is more like light bending. When it enters water from air, waves travel along the interface, the boundary between different rock types. They are bent or refracted as they go. This technique tells us something different. It reveals how fast waves travel in each distinct layer, helping us identify the materials lurking below. How do we create these initial signals? The tap on Earth's drum. On land, geophysicists might use a heavy weight dropped precisely, or a specialized, powerful truck that vibrates the ground rhythmically, sometimes very small controlled explosions, buried just beneath the surface. The key is a sharp, clear energy pulse. Safety, of course, is always paramount. Out on the open ocean, the challenge is a little different, but the principle remains the same. Research ships tow an energy source. Often it's an array of air guns. These release bubbles of compressed air, creating a potent sound wave in the water. This wave travels to the seabed, and then deep into the crust below. Chains of hydrophones also towed. Listen. What have these echoes shown us? Countless wonders and vital resources, vast reservoirs of oil and natural gas, the very fuels that built our modern age. They help us find hidden aquifers, underground rivers of fresh water, essential for drinking, for agriculture, especially in arid, thirsty lands, and sources of geothermal energy, tapping Earth's own inner heat. But seismic exploration sees beyond resources. It illuminates the Earth's dynamic processes. We map hidden fault lines, the fractures where earthquakes are born. This knowledge helps us build safer cities to better withstand nature's power. Scientists study the deep crust, even the mantle far below, unraveling the story of plate tectonics, learning how our planet formed and evolves. The benefits are truly immense. Smarter, more efficient resource management, reducing the environmental footprint of exploration, safer communities, better prepared, and a profound, ever-growing understanding of this beautiful, complex world we inhabit. It minimizes the guesswork, saving time, saving money, and helping us protect fragile ecosystems by targeting our efforts precisely. The journey into Earth's depths continues. The future of seismic methods is bright. New technologies are emerging, creating ever sharper, more detailed images. Think of three-dimensional seismic surveys, or even four-dimensional, adding time. 4D allows us to watch changes, like monitoring fluid movement in a reservoir, or tracking magma beneath a volcano. Earth still holds many secrets, and our quest to unveil them, powered by science, marches on.